Well, let's go over to, I have a place to draw that here. So the Thevenin equivalent circuit is basically the goal of this process. So it's a very simplified circuit. It's you take a complex network and a component, which in this case are R3, and you basically create an equivalent circuit as far as the load is concerned, or as far as in our case R3 is concerned. This is what the rest of the circuit looks like. R3 doesn't care how complicated your original circuit is. All it sees is a very simple set of values, current, resistance, and voltage available. So let's just see what that might look like. So the Thevenin equivalent circuit, and I often do draw this before I start, because it kind of helps me remember what I need to find. So if I haven't done Thevenin in a while, I might need to remember, oh yeah, I need to find Thevenin, I need to find Thevenin, and then what do I do with those numbers? Well, Thevenin's going to go right here. That's going to be the source or the supply, the most available, or the most voltage available to R3. Now the rest of the circuit resistance, or the resistance that the load sees when it looks back at the circuit, is going to be Thevenin, so that number is going to go right there. And then R3, finally we get to do something with R3. Okay, well there it is. There's where R3 is going to exist, and now we can solve for R3. And R3's original values, 2k ohm, and now I'm going to go grab my Thevenin number and my Thevenin number. Before I do, I want to show one thing. Okay, so the current in this circuit, or the current that the load sees, is going to be the actual current that it would see in the original circuit. Now that's what's cool, is now all I have to do is solve this little circuit, and the voltage that the load sees is going to be the voltage that it sees in the original circuit. So I solved this little circuit, and I know what R3 is doing in my original circuit, which is pretty handy. There's a lot of things that I can figure out. I mean, basically I can switch out any component in a complex network, and I don't have to solve the complex network. I only have to solve this little series circuit, which makes life easy when you're going to do when you're trying out several network configurations or loads or whatever it is that would go in your circuit between point A and B. Alright, so let me go grab my values and we'll get started, or we'll get finished, I guess. Alright, so my original, or my Thevenin, was found to be 824.6 ohms. Okay, so I'm going to go put that in where it goes. 826.4 ohms. I think that's what I said. Now this is a common mistake. I write things down. 824.6. 824.6. Is that what I got? No? That's my favorite, one of my other favorite mistakes. 824.6 ohms. And let's go get Thevenin and try to copy it down properly. Thevenin, 20.61 volts. 20.61 volts. Okay, 20.61 volts. Now all I have is this little simple circuit to calculate. The thing that I care about is the current of R3 and the voltage of R3, and then I'm going to plug that back into my original circuit, and we'll see how it goes. So let's just do it. So I can find the totals of this circuit. So RT equals, now if you have quicker methods for solving this, go right ahead. I just like to show all the steps. So RT is going to be Thevenin plus R3 in this case. So let's say RT equals, now this is, you can see why I do clean sheets of paper, because I've labeled R total at least twice on two different pieces of paper here. and they mean different things. They're not related necessarily. Okay, so our Thevenin was 824.6 ohms plus 2.2k ohms. Okay, so now RT should be, what would it be, like 324 or 3024.6. Well, let's bring the old calculator back. Come on, calculator. Let's do this calc. Let's do this calculator. 824.6 plus 2.2k. See if my mental mathing was close. Yeah, pretty close. Calculator rounded it off. I'll go ahead and use that number. 3.025k, or just 3025, which actually is simpler to write, but there it is. Okay, so now I can find IR3, and I could call it I total, but I've already labeled it as IR3. It's nice to know what that number actually is, and it relates to our original circuit, and I'll show you that in a second. IR3 is going to be V Thevenin over that R total number that we got. IR3 equals the V Thevenin, the most voltage ever available to the load resistor. So let's look at it. 20.61 volts would be the most voltage I could ever see there. So if I had a 10 meg resistor for R3, it would see 20.61 volts roughly. Okay, so let's see, our total was 3025 ohms, and let's go ahead and solve that. IR3 equals, bring the old calculator in. I'm going to take my 20. Actually, let's go up here. I've got a pure number up here. That number, less rounded, divided by our resistance, less rounded, is 6.815 milliamps. Alright, so there's my actual current for R3 in my original circuit. So I would see that current right here. Okay. And I'm going to show you that in a second. So now I'm going to find that voltage for R3. And there's some double checking methods I could do here. I'm getting excited, so I kind of want to solve the circuit and see how it goes. VR3 is going to be IR3 times just the value of R3, whatever it is. Okay, so VR3 equals that 6.815 milliamps times, alright, let's see, times the value of R3, what is 2.2k ohms. VR3 equals, alright, here's the moment of truth. Well, this isn't the moment of truth, but this is basically we've got a number. Okay, enter, times 2.2 e to the third, whoa, enter, times 2.2 e to the third. Okay, it looks like I got it all in there. So I'm getting about 15 volts, 14.99 volts. Okay, so that number and this number are what I should see in my original circuit. Should we try to solve it? We could solve this one traditional. Let's just do that.